Thank you for giving me the opportunity to present at this great conference. So I work on the simulations of moist convection on rocky tidally-locked planets, and this is the work I've been doing with Hugo Lambert and Nathan Mayer at the University of Exeter, and also Ian Bootle at the UK Met Office. So today I'm going to remind you what the circulation looks like on a tidally-locked rocky exoplanet. I'm going to show you some how important the dayside convection is for the global climate of these planets. I'll talk briefly about some challenges in modeling convection in terrestrial atmospheres, and also show you some exciting results of convection resolving experiments for these planets. So, what planets have been looked so far? These are well-known terrestrial exoplanets, namely TRAPPIST-1e and TRAPPIST-1f, but also Proxima Centauri b. And as you can see from this table, in terms of their orbital and size characteristics, they're fairly close to each other, but they do vary in terms of their rotation period, and of course TRAPPIST-1e receives more radiation than TRAPPIST-1f, while Proxima b is quite close in this regard. And so for this simulations, I just assume for now an Earth-like atmosphere, which is nitrogen dominated, with water as a main condensable species. And I ran this as an exoplanet simulation with a slab ocean at the bottom. So imagine this rocky exoplanet orbiting an M dwarf. We can imagine represent the circulation on such a planet using a schematic. So this is a vertical cross-section along the equator on this planet. And you have the solar radiation coming from its host star to the dayside of the planet, and then the planet loses heat in a form of long-wave radiation from both dayside and nightside. And this strong heating at the dayside and the heating of the surface of the planet makes the atmosphere convectively unstable, and this leads to the rising convection motions on the dayside and the formation of a thick layer of clouds. And this heat and moisture transport eventually merges with the upper atmosphere equatorial jet and is being transported to the night side of the planet. And in the absence of the dynamical ocean, this atmospheric heat transport is, of course, the only source of energy for the night side. And this is indeed what we see from a GCM output. So this is a UK Met Office unified model output for TRAPPIST-1e. You have the very warm atmosphere at the surface on the day side of the planet. Let's zoom in where all the interesting stuff is happening. Then if you plot the wind vectors over it, you see the rising oceans, and then the eastward jet. And when if you overlay that with the specific humidity contours, you see how it's concentrated on the day side where all the evaporation is happening. And then if you rescale it to logarithmic scale, you see that it eventually is being transported to the night side as well as clouds and heat. So for a situation like that, you can hypothesize that convection should regulate the climate on a tidally-locked planet. And how can we test this? So we can run again this 3D GCM with different options for convection. So we can use a sophisticated mass flux convection scheme, which is used for weather and climate prediction on Earth. And I'm going to call this experiments control. And then we can use a simple moist adjustment scheme, which I'm going to call LCS for Lambert and Lewis convection scheme. And then I can also switch off the convection scheme completely, and then let the model handle the convection itself without any help from the parameterization. So in the next few slides, I'm going to show you the few global maps of surface temperature for control simulation and also sensitivity runs, both for TRAPPIST-1E and Proxima B. So starting with TRAPPIST, this is the global map of sea surface temperature, or just surface temperature, and you see that of course the day side is much warmer than the night side, and the difference is quite large. And you have this cold traps on the night side where the Rossby gyres occur in the wind field. For Proxima B, in these conditions, the situation is fairly similar. And then when we run this simulation with the simple adjustment scheme instead of the mass flux scheme, you see that it has quite a significant impact on the surface temperature of the planet. So the night side especially warms significantly by up to 40 degrees for the TRAPPIST-1E case. However, then we can also run a similar sort of simulation, but now switching off the convection scheme completely. And this is the simulation result for TRAPPIST-1E, and it's a fairly similar picture. You have the slight cooling of the day side and warming on the night side. However, for Proxima B, the situation is almost reversed, and you have the night side cooling quite significantly. So for these two quite similar cases, you have opposite effects by just swapping a convection scheme to a simple one, or switching off completely. And this is interesting, and I'm still trying to wrap my head around why this happens. But looking at the large-scale circulation, so you see that, so this is horizontal wind speed shown by vectors, and the magnitude of the wind is shown by colors. And this is so this is the equatorial jet, and then it splits into two branches around the substellar point, and then it merges again near the eastern terminator. And the situation is similar for both planets. Then when you switch off the convection scheme, the Proxima B simulation doesn't change much, and the magnitude of the wind stays fairly similar. But for the TRAPPIST-1E, the large-scale circulation changes quite dramatically, and you don't have this branches around the substellar point, and instead you have a very strong equatorial jet, and you can expect that because the wind speed increased at the eastern terminator and decreased at the western terminator, the net moisture export from the day side is larger. So this is likely the biggest contributor to the change in the night side conditions, while radiation and turbulent fluxes on the night side are probably cancel each other out and play a minor role. So, yeah. So the sort of take-home message one is that convection in GCMs regulates the climate not only on the day side, where all the convection is happening, but perhaps counterintuitively on the night side. And also the second take-home message is that using a simple convection scheme can have different effects for different planets. So why modeling convection has such a big impact? Well, because as we heard from Alison this morning, modeling convection is quite challenging. It has a lot of feedbacks, and also involves a wide spectrum of spatial and temporal scales. And so it is computationally expensive to run global circulation models at a convection resolving resolution, especially when they're coupled to radiation and chemistry and other stuff. So what we do, we run these GCMs at very coarse resolution instead, and so all the convective processes fall into subgrid scale size, and we have to use parameterizations to account for the net effect of them. But unfortunately, we don't have any in situ measurements on exoplanets, at least not yet. And so we have to, our next best option to test these parameterizations is to run a convection resolving model at a very high resolution, which does not need a parameterization to handle convection. So this is what we can do with the unified model. And we use a global model, just as I showed before, as a parent model to supply boundary conditions. But then we put a nested grid inside of that model and run this model at a much higher resolution. So I'm using sort of convection permitting resolution of about 4 kilometers. And in this case, of course, we have convection explicit, so the convection parameterization is switched off. When we look at the output of these simulations, so this is so far just the global model again at a coarse resolution with convective parameterization, and this is just a chunk cut out of the global model around this nested region, and you see that in terms of updrafts, the rising motions, the upward velocity field is quite washed out and weak. But when we run this model at high resolution, you can start to see all the convection cells, individual convective cells being resolved, and also some mesoscale circulations emerging on this planet. And also the magnitude of updrafts and downdrafts is much greater than in the global model. And this is what it looks like in terms of cloud fields. So this is the reflected shortwave radiation. And you see again that the convection resolving simulation gives you a much more detail and much more inhomogeneity in terms of cloud field. And this is what the precipitation looks like. So precipitation falling from these convective clouds. Okay, but does it make a difference for the mean state of the region? And actually, I should say that the global model with this mass flux convective parameterization is doing a pretty good job, at least for Earth-like atmosphere, in accounting for all the subgrid convection. And so, in terms of temperature or specific humidity, overall the curves are quite similar to each other so the curves from the global model and the regional model. And the biggest differences are actually in the structure of the clouds on the day side. And you can see this in terms of cloud condensate. So this is average vertical profiles of cloud water on the left and cloud ice on the right. So this is from the global model, and this is the orange curve is from the nested run simulation. And you can see that the global model overestimates the cloud water and underestimates cloud ice. And this can have an impact on the radiative forcing of the clouds, and also it can impact the formation of rain or snow precipitation. Another take-home message is that compared to convection resolving model, GCM may incorrectly represent cloud structure and their radiative effects on the day side. But I should say that one caveat of our study is that we use this model in a one-way nesting setup. So even though the regional model has the boundary conditions from the parent model, there's no feedback to the global model from these high-resolution simulations. So one way to account for this impact is what I'm suggesting to do is basically what I'm doing now is to run a series of global experiments with different convection schemes, then calculate the flux of moisture, upward flux on the dayside as a metric for convection, and then somehow find a correlation with some night-side parameters such as the minimum temperature or the amount of moisture on the night side. And if we find a good correlation between these parameters, then we can run a nested simulation, find the same integrated vertical flux of moisture, and then infer from that what difference would it make for the night side if we run the simulation as a convection resolving model for the whole planet. And with this, this is my final take-home message. So these simulations, high-resolution simulations, may be used to assess the convection schemes and their impact on the exoplanet's climate. And this is the summary of the messages. And with this, I'll leave you. Thank you.
Is there some question? Yes, two questions in the front.
Hey, Daniel from MIT. This is very exciting. Do you have a way for understanding the different schemes, maybe in terms of a convective detrainment or entrainment? Have you thought about that?
Yes, I'm thinking about that. And one of my next step is to run a series of sensitivity experiments for the mass flux scheme and just change entrainment and detrainment parameters. Because for Earth-like simulations, for simulations of Earth convection, it has been shown that this is indeed probably the most important parameter in the convection parameterizations. But we also have a sort of a statistical framework in the making by Hugo that can help us to understand the differences between completely different convection schemes. So we can probably apply that too. Yeah, thank you.
Nice talk. Tad Kamasik, U Chicago. So how do you choose the scale for your nested box? Have you tried like different box sizes? Does that affect the convection on the dayside?
Yeah, that's a good question. And I've spent like many months of simulation of trying to shift that box around and see what difference it makes. Basically, well, first of all, you have to probably choose the position correctly, because on some planets the hotspot is shifted a bit to the east, and this happens on terrestrial planets as well. So you should account for that. And also, of course, the smaller box is in the simulation, the more this regional model is sort of dominated by the boundary flow from the parent model. So you have to make this box sufficiently large. So far, it's around 60 degrees in the side of the box, and it seems to be sufficient. But yeah. Good question.
One very quick question.
Martin Turlbet from Observatory of Geneva. Did you make some experiments for slow rotator synchronous planet, and do you see any indication of self-aggregation in these simulations?
Yeah, that's one thing that we're thinking about too. But I would say that it's probably not exactly self-aggregation, because there are so many external disturbances that can affect us. So the convection probably organizes, but it's probably not exactly self-aggregation, because you have quite a large wind shear in over this region. And
but yeah, the wind shear is because the planet you are looking at are quite fast rotator, right? But yeah, what if the planet were much slower rotator? Did you explore that?
I haven't looked at super slow rotating planets, but yeah, that's a good idea. Thank you.
Okay, let's start again.